Welcome to the Tech Talks Daily Podcast, where you can learn and be inspired by real-world examples of how technology is transforming businesses and reshaping industries in a language everyone can understand. Here is your host, Neil C. Hughes.
Welcome back to the Tech Talks Daily Podcast. Now, as you all know by now, I get incredibly excited quite easily, and today is one of those days where I've encountered two things that have made me excited. Where is he going with this, I hear you say? Well, first of all, I've discovered a new podcast player that I can embed on my blog posts that will transcribe the episodes for me so people can follow along and read and get information out of there without me having a 8-page transcription that ruins an entire blog post. So I'm going to be playing with that over the next couple of days, and I'll let you know if it is any good, or maybe you can check out this episode and you let me know what you think. And I also discovered a company called AKHAN Semiconductor, who are ushering in a new era of computing technology, but with diamonds, specifically targeting the needs of a smartphone, wearable, automotive and VR systems. The concept blew me away because I must admit, I didn't really know this, but from phone screens to semiconductors, military defence capabilities and self-driving cars, a diamond can be applied to a number of different technologies to make them operate more efficiently. Because a diamond is stronger and harder than industry standard smart screen glass and runs much cooler than silicon, which is the traditional material used for semiconductors. And currently, companies such as Lockheed Martin are using diamond to enhance the survivability of fighter jets and drones. If that doesn't sound like an exciting and intriguing subject, I don't know what is. So please, buckle up and hold on tight so I can beam your ears all the way to San Francisco, where we can speak with Adam Khan, CEO and founder of AKHAN Semiconductor, who's going to be talking with us today about how diamonds are grown and what ultimately differentiates them from jewellery, and how they're planning to use diamonds in the next generation of technology. So a massive warm welcome to the show. Can you tell the listeners a little about who you are and what you do?
Certainly. I'm Adam Khan, the founder and CEO of AKHAN Semiconductor. My background is in condensed matter physics and semiconductor device engineering. I founded in late 2012 AKHAN Semiconductor in partnership with the Department of Energy and Argonne National Laboratory. AKHAN is squarely focused on enabling a diamond age of electronics. We're the global leader in diamond semiconductor. This includes things like semiconductor optics for your protective coatings for your smartphone, high-quality laser optics, as well as traditional semiconductor electronics, power circuitry, inverters, and temperature management.
I'm really excited to get you on the podcast today, Adam, because after reading how you're ushering a new era of computing technology, but with diamonds, it's incredibly exciting, especially because you're specifically targeting the needs of smartphone, wearable, automotive, and virtual reality systems. But can I ask you to set the scene and bring everyone listening up to speed by explaining the importance of diamonds in the tech industry? And also, I've got to say, why diamonds could be a geek's best friend, never mind a girl's best friend, right?
Absolutely. So I think the problems that we're experiencing, whether you're talking about smartphone, computing, any type of electronics, it essentially boils down to the same problem. The materials that we're using today really are reaching their limits. Whether you're talking about silicon, not attaining a fast enough clock speed or being able to perform without overheating, or if you're talking very simply about your phone, every time you drop it, the screen breaks, cracks, very prone to failure due to simple user interface. So diamond has actually been known for a long time to have some very favorable material properties, namely the ability to handle heat much better than copper, which is the de facto heat sinking material, about 5 times better, and over 22 times better than silicon, the current electronics material. Beyond that, diamond also allows us to handle much higher power levels in much thinner profiles. So this is the so-called power efficiency of diamond. With about 1/1000th of the same material, we can handle the same level of power. So you're talking about far thinner profiles in our circuitry. You can also operate at much higher frequencies. We hear about this 5G infrastructure being discussed very prevalently, the move from 4G to 5G in this next sixth generation. So we're always going to higher bands of frequency, and we're always using a finer part of that bandwidth. So Diamond allows us to move to higher frequency circuitry, which is necessary for this technological progression. On the consumer electronics side, we see, our phones for a long time kept getting thinner and thinner and thinner, and then all of a sudden they had to start getting thicker again. Well, this is twofold. One, the amount of circuitry that are in our phones has gone up dramatically. Instead of just being a phone, as we know, we stream videos from it. It has to be connected to Wi-Fi, camera. There's a tremendous amount of circuitry densely compacted into a thin area. The flip side of that is to make our phones harder and stronger, because glass really hasn't improved since the 1960s. We've always had to increase the weight of the glass on the phone to improve its rigidity or structure. Now, combining with diamond, which is the hardest material known to man, it's the hardest on the most hardness scale, and also a very strong material, we're able to marry this with traditional glass to make much thinner profiles that are stronger, more rugged, but still very cost effective.
And you said cost effective now, and I think that'll be a bit of a surprise to a lot of people listening, because like you said, it is the ideal material for devices with a screen, including smartphones, VR goggles, and even self-driving cars. And I completely get that, but it's cost effective and not expensive like you would automatically assume. Is that right?
Absolutely. So we're dealing with lab-grown diamond, and diamond's often a misnomer because people think, jewelry, diamond, very expensive. It's a luxurious material. It's a very useful material, but the way that we grow diamond is actually a nanocrystalline diamond. So this is a thinner form and a nano version of this bulk diamond material. We're able to grow this from a methane precursor. People often say, silicon is very cheap. It's derived from sand. Methane is the most abundant molecule in the universe. So it's a very cost-effective way to tap into this material. And we're also able to grow diamond in very large area, like you'd see in wafer technology. So this means a very thin layer of diamond over a very large area. And in terms of the cost, with respect to electronics, there's a competing material, gallium nitride, which is being used quite heavily now in power electronics, laser optics. It's one of the potential successors to silicon. Diamond is actually cheaper than gallium nitride and can be processed much easier. From the glass side, we have sapphire. Sapphire was a material that made a big splash. It's on all of the Apple watches. It's on your camera cover lenses. It's a very hard and strong material. Sapphire, the problem there is you're not able to make it in a very large area. Diamond, which is much harder and much stronger, can be made in very large area, and it's cheaper than sapphire. So in terms of the performance and the cost, we're better than the next successors in both of these respective markets.
And just so everyone understands exactly how it would work, can you tell me more about semiconductors and also how the diamond is able to handle these higher voltages, especially when compared to traditional silicon without deteriorating? And new devices, assumingly, will be available for high-power applications soon, like quantum computing. Is that right?
Absolutely. So semiconductor, as the name implies, is somewhere between a conductor, like a metal, and an insulator, like a glass. The ability to modify the structure to tune any kind of energy input is extremely important. So if we think about this from things like conditioning power, going from higher voltage inputs, conditioning it down to lower voltages, things like light, incoming light, tuning the transmission of that light, potentially modifying the wavelength. These are all different examples of what the semiconductor can do in terms of optics and electronics. So diamond is really interesting because diamond arranges its atoms, the carbon atoms, very similarly to both silicon and germanium, the prevalent historic semiconductor materials. What's different about diamond is the carbon atoms are much closer together, much more tightly bound. And this gives rise to these extreme properties. Because the bond is so strong, the carbon-carbon bond, valence bonding in diamond, it's one of the strongest known bonds in the valence bond. This gives rise to these extreme properties such as the high hardness and high strength. The carbon atoms are very resistive to any kind of macro change or pressure applied to them. Because of that, also, the electrons in diamond and graphene, a related material, are moving extremely fast. Diamond is the 3D material and graphene is a 2D material, but they behave very similarly in terms of their extreme properties. So when we think about electronics, we think that it has to provide a high electron speed from a material perspective, but it also has to be able to handle heat in a very effective way, because heat will generate loss in our electronics in addition to failure. So graphene being a very heat-effective material and diamond being a very heat-effective material actually work very well together. And this will touch upon things like within our consumer electronics, allowing our phones to continue to increase in terms of their capability without overheating in thinner profiles. And in terms of quantum computing, which is, I think, a little ways away in terms of being developed, this will allow the structure to be tapped into, the diamond lattice structure, to manipulate these type of optical defects to really allow quantum computing to expand. Right now, quantum computing is largely limited to manufacturing this diamond with the nitrogen vacancy center in it. It's a very intensive process, and above and beyond that, you have to keep these systems quite cool. You're typically cooling these with below liquid nitrogen temperatures, less than 77 Kelvin. So really, to enable quantum computing to be widespread, we need to be able to better manipulate the defects inside of the diamond, and that's one part of what AKHAN is working on.
And before you came on the podcast today, I had to do a little research. And on doing that, I quickly learned that it's also used in military defense too, because of diamond's ability to act as this multi-layer anti-reflective coating system. And how my understanding is it becomes critical in the military aerospace sensors and also the detector applications too. But can you expand on that? Because it's fascinating.
Absolutely. Yeah, there's some interesting use cases within military and aerospace, particularly with laser and electromagnetic weaponry. So if we think about it from an offensive perspective, this is where we want to send a very high power laser to target things like incoming ballistics, craft, or things potentially ranging in distance. So the laser is quite effective at hitting these targets. But the problem is to generate a high enough laser energy density, you have to focus many laser beams into a very fine area. And now comes the problem where, what do you do with the heat that's passing through these systems? Because optics are typically made from glass or infrared materials, which are not very heat effective or resistant to what's called thermal shock. So incorporating diamond in these thin systems allows the laser beam to pass through and to remain cool without overheating the structure before it exits the aperture, meaning that you don't want to turn on such a high power system and have it fry within the first few minutes of use due to some optics failure. So diamond being a very efficient heat material, but also being very transmissive in infrared and visible wavelengths, makes it very favorable for offensive. And that's been known for some time. What AKHAN has really specialized in most recently is protecting against these laser systems. Here, where you need a countermeasure to protect against this high energy in a very tight area. And here's where the rub really arises. One would think that it'd be better to reflect this incoming wavelength off. But the problem is if you had a mirror, particularly on like an aircraft or something like that, the mirror would blast right off from the laser intensity. And also, in order to make it effective, you'd have to make it quite thick, which adds weight. The diamond multi-layer system, which we've are the first to develop in partnership with Lockheed Martin Missile and Fire Control Systems, demonstrates for the first time a very thin layer of diamond. We're talking on the order of 100 nanometers, 1/10,000th the thickness of a human hair, being able to withstand the state-of-the-art laser density for the first time. So not adding any system weight virtually, but being able to defend against the state-of-the-art in terms of laser weaponry today.
And if we zoom out from the topics we've just discussed there, can you tell me more about how these lab-grown diamonds are actually revolutionizing modern tech? Because it's something that we don't see in the familiar tech headlines and tech buzzwords now, is it?
No, absolutely. And great point, because from AKHAN's perspective, when we say we're enabling a diamond age, what does that mean? This means that the material of choice becomes prevalent in all that facets of technology, some that we see every day, like our phones, and some that we don't see, like satellite telecommunication and infrastructure. So the ability to tap into diamond in terms of power transmission will affect the infrastructure side. The ability to make more energy efficient electronics will obviously affect our consumer electronics, but also in terms of scientific computing and industrial computing will advance those causes, the supercomputing platforms. And with respect to automotive, we have the same kind of problems we have in aerospace, where we have to make these systems lighter and more effective, but also cool the same level of electronics. And the problem becomes even more so when we talk about electric vehicles or hybrid electric, plug-in electric vehicles, because you now have very heavy power electronics, which also need to be cooled. So everything from our cars to our phones to what the technologies that keep us safe, Diamond has a real role in, and we're now seeing a very compelling use.
So when we're talking about AKHAN Semiconductor and playing that role in ushering the new era of computing technology with diamonds, I've got to ask, what kind of areas are you specifically targeting? Because it sounds like you're casting the net quite far and wide.
We are, and we're tiering our rollout based on the use case. So we've entered the market within our consumer electronics and aerospace technologies, and this is largely on the optics side. And as you'll see over the next 24 months, more of our electronics components will start to hit those two respective markets. Here, because the biggest issues that we're seeing from a consumer or user in these market spaces that, again, our phones are cracking very easily after being dropped, or in AR, they're overheating, or in aerospace, from optics perspective, these are all very near and prevalent issues that are currently facing. With power electronics, we see that this is a longer lead time to insert into these markets. So this is why, as we continue to develop the technology, we're staying aligned with the automotive platform. Things like the most advanced quantum computing and supercomputing, and perhaps the logic side, a diamond-based processor, these are further out problems, and these require obviously more development. But this speaks to the longevity of our technology roadmap rather than us trying to go after everything in one shot.
And what are your biggest challenges right now?
I think from our perspective, it's somewhat unusual in that we have such interest from all of the target markets. The technology that we're developing, is really showing effective use in some of the problems that these customers are seeing. From our perspective, I think the issue of scaling up fast enough will be something that we're addressing, because obviously consumer electronics volumes are quite vast. Over 300 million iPhones were sold last year alone. That's one market provider with one product line. So selling into that market and addressing and servicing that market probably is an animal in and of itself. Aerospace has obviously much lower volumes, but the bar for those technologies, the performance level is quite high. So making sure the sophistication of the technology, the quality of the technology maintains in delivery. This is really where we're pouring our focus into, servicing these very valuable markets to the best that we can, without overscaling or scaling up perhaps too quickly and cannibalizing ourselves. I think one interesting example, particularly competing material, sapphire, that was simply the case where Apple had a big interest in this material. The provider could not scale up fast enough, and that ultimately ended up bankrupting that company. So there's obviously a cautionary tale and something for AKHAN to learn from while bringing this new material to the same market.
And from the outside looking in, it looks incredibly exciting, I've got to say. But I'm curious, what excites you about the future of tech, and also, of course, the role that AKHAN Semiconductors will actually play in that future?
Great question. And from my perspective, the thing that I'm most excited about is enabling the next generation of great technology. Cell phones, as they say today, really have been constrained from a design perspective. They can't go any thinner because they have to have a very rigid structure, and they have to get rid of this heat, and they have to have the next generation in terms of performance. So that's really something that's been limited. And it's the same thing with aerospace and with automotive. These platforms have been constrained and really underpinned by the silicon technology. So I'm really excited not only to introduce the technology, but to see what the next generation of these platforms can do. To have phones that are now more thin, that have more functionality. We just saw foldable. That's been known for some time, that the supply chains have been preparing and investing in this foldable display. One thing that isn't talked about, which will come to pass in the next 10, 15 years, is stretchable display. And so enabling the platforms to allow our phones not only to fold, but to stretch, and now having thinner technologies. And I think this is why anybody in technology gets involved. We are fans of it, and we want to see what can be the next if just these bottlenecks can be alleviated.
Well, I've got a feeling there's going to be a lot of people listening to this podcast today wanting to find out more information and learn a little bit more about this. So can I just ask that you let everyone, or point everyone in the right direction of where they can find you guys online, and also contact your team if they do have any additional questions after listening to us today?
Sure. Well, you can visit our website, akhansemi.com, AKHANSEMI.com. That is our website. All of our materials are available there in terms of the news, the technology, and many of our white papers are available on the Material Research Society, Cambridge University Press, and many others.
Excellent. Well, I'll add all those links to the show notes over on my website, techblogwriter.co.uk. But more than anything, just a huge thank you for coming on and taking the time to talk me through this. I love the work that you're doing and how you're enabling this diamond age of tech. It's incredibly exciting. So a big thank you for coming on and joining me today, Adam.
Thank you, Neil. Appreciate the time.
Consider my mind officially blown. I mean, if we just look at the world of consumer electronics, where diamond ultra hardness and ability to run thin makes it the ideal material for all devices with a screen, including smartphone, VR goggles, and even self-driving cars. But in particular, semiconductors is where it gets exciting for me, because diamond is able to handle higher voltage than traditional silicon without deteriorating. Meaning new devices will be available for high-power application, such as quantum computing. And that, my friends, is where things get very exciting. But hey, over to you. Please email me, techblogwriter@outlook.com. And if you go techblogwriter.co.uk/AKHAN Semiconductor, you should be able to find today's episode with this new podcast player and transcription. So see what you think of that as well and let me know. So remember, you can also get me on all my social channels are at the bottom of the website too. So let me know what you thought of today's episodes, what you think of the new podcast player. And I'm going to try and bring myself down a bit now with a nice cup of hot chocolate, because I'm getting old. Too much excitement in one day will finish me off. So a big thank you for listening. And until next time, don't be a stranger.
Thank you for listening to the Tech Talks Daily Podcast with Neil C. Hughes. Remember, technology works best when it brings people together.